Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering in this video lecture is Monte Carlo and temporal difference methods, which is topic number 12 in the list of topics covered in this course. And the subtopic is A. So the lecture is 12A, that is the basics of Monte Carlo and temporal difference methods. Now, this video uses the supplemental website accessible at www.easymcq.com/GoGet, which is a personalized learning management system. So, what is the future of content delivery? That is not the future alone, that is also the present, because there are literally hundreds and millions of end users who are getting educated using the content delivery platform and mechanism, which are in hundreds and millions. So, that is the approach which is being used in delivering and explaining the concepts in this course. So, the personalized learning management system is accessible using the URL which is given in green color, and the content delivery mechanism is explained using 6 videos, and those videos are accessible using the link given in blue color. So, what are those features which I've mentioned? These features consist of advanced and basic content search, which is not there in leading learning management systems. And then, of course, the ability to support people with visual disability, such as changing the font size, color, line spacing, and so on. And then this content is organized in such a way that it can efficiently use the limited speed, the limited space, and the speed of a handheld device. And of course, you can track your progress, what you have seen, done, and what you need to do. And then, of course, you also can test yourself online in real time, your knowledge assimilation and knowledge capturing. So, how the content is delivered? The content delivery can be question and answer based, and it can be traditional slides based. Now, the question and answer based approach is engaging, is proactive, it promotes thinking, and of course, it is very productive also. And the traditional approach contains a lot of details. So, the approach we have been following in this course is a blended approach, which is the best of both. So, this is the list of topics which are covered in this course, and we are at topic number 12. And this topic is further divided into concepts in the form of question and answers. So these are in front of you. So the first set of question and answers, which is 12A, is shown with a yellow background, and the next set of Q&A in the form of concepts with a green background. So now we move on and start with the lecture. Well, so we start with the lecture 12A, which is deep reinforcement learning and Monte Carlo and temporal difference methods. So, what are those methods? Okay, and before we go into them, a little bit of a background. Okay, so now we have this. Let me explain this to you. What does this mean? So we have these squares. Okay, and within these squares we have a circle, right? And then within each square we kind of put down randomly the points. Okay, so here we have no point, a black dot. Here we have 250, 2500, and then 25,000. So I'll explain this to you. So now the thing is that we are working towards a deterministic quantity. Okay, and how we are looking at the deterministic quantity by using probabilistic methods. Now they go back to 1733, if I'm not wrong, if my memory serves right. So this method was devised of calculating the pi. Okay, how it was done by dropping a stick or a needle on a floor. Okay, so we still look at in the same way the Monte Carlo approach to estimate the pi. So suppose there's a unit circle which is drawn within a square, as you can see, and the points are chosen randomly within the square. So this can be looked as a dart board in a square frame with the darts thrown from a distance. Now understand that the area of the square is 4, okay, and the area of the circle is pi. So the proportion is pi over 4 of the darts will fall within the circle. So this we can observe in the figure also, okay. So this is how it works. So there's a relationship between the randomness and how much that randomness is going to be. So the Monte Carlo methods bring that simple yet powerful approach to learning in deep reinforcement learning. And this is used in empirical or experience based estimation. And how? Because by relying on sample returns. So, based upon this model which I've shown you, so we don't need any explicit models. So, that makes this approach ideal for complex environments without using the models. So, this episodic structure provides complete feedback about the long term value of the actions. Okay, because it depends upon how much darts have been thrown, and that's going to return a kind of average that reduces the variance in estimates that promotes stability. Now, this is different from what we have studied before, but these strengths have limitations like delayed updates and high variance from episodic sampling, and of course, inefficiency in large or continuous domains. So, these methods, Monte Carlo methods, are often like they need to be augmented or hybridized with other techniques such as deep reinforcement learning that forms the basis for more complex, sophisticated, and useful algorithms that retain Monte Carlo's core insights while overcoming its drawbacks. So these are the so this is the background. So what we are going to cover is an estimation which is based upon the sample, and there's a relationship, and we get that relationship of which we discussed which is pi over 4 without having a model, and then there's episodic learning. So episodic learning is the learning which is based upon the episodes or individual experiences, and the return averaging. So we will discuss all of this. Okay. So what is meant by return averaging, and uh, what how to use it. So first we start with the sample based estimation. So what happens in sample based estimation? Monte Carlo methods basically estimate the value functions by sampling complete episodes, okay, prior experiences, and using the actual returns observed to update the policies or value estimate. Policies we've covered in videos number 10, which is reinforcement learning. So there is no model. So these approaches do not rely on models of the environment, which of course has a processing power requirement. So that makes it ideal for real world or high dimensional tasks. Now, what happens in deep reinforcement learning? That the samples returns they like serve as targets for neural network training. But remember that this sample based method can be data intensive and it may suffer from high variance. What is variance? That is covered in statistics. So, especially if the policy is still under exploration or the environment is unstable, that's the issue. Okay, so we move on to episodic learning. Episodic learning. So, Monte Carlo updates occur only after an entire episode ends. Okay, so that allows the agent to observe the full consequence of its actions, whatever has been done. So this ensures unbiased return estimates, which is important in deterministic environments. Okay, but in deep reinforcement learning tasks, if there are long or if there are indefinite episodes, this can cause significant update delays and it can result in slow convergence. So, but still, episodic learning is simple, it is intuitive, and it works well in settings. Which type of settings? Where clear terminal states provide meaningful feedback. For example, like games and navigation. So the the feedback is clear. So what is return averaging? Return averaging. So return averaging in Monte Carlo methods involves computing the mean of all returns observed from a given state or action. So what is the advantage? This helps uh, smoothing of the noise. It reduces the variance and stabilizes the learning. And this is particularly important when using functions approximators in deep reinforcement learning, because what we have said we're now basically trying to approximate the functions. Okay, so in deep reinforcement, so like while this is useful, it may require visiting the same states multiple times. Okay, but which is like often unlikely in continuous or high dimensional environments. But still, this concept underpins variance reduction techniques like baselines in policy gradients, and the key is training stable policies. So we are keen about the stability here. Okay, so I would suggest that you read the details here. Okay, these are the details, and you should, some calculations are also here. Okay, and then if you're more interested, here are the references. All right, so we move on to the next Q&A or the concepts. So first was about temporal. So first was Monte Carlo, and now temporal difference learning, and what it is and how it is different from Monte Carlo methods. So there are a number of differences. For example, there are bootstrap updates. What they are, that's why I'm going to explain. Then this is kind of incremental or step-by-step learning, and then of course there's the adaptability also. So these are the details which we will be covering. So a little bit of background. Okay. So these temporal difference learning brings the best of the Monte Carlo methods and dynamic programming, which we have already covered in topic number 10. So learning from experience, okay, and then we have the bootstrapping, which is based upon the current estimates. Now, recognize that the bootstrapped updates allow for fast and incremental improvements with step-by-step learning without requiring full episodes. So that takes less time. Although the step-by-step learning enables efficient memory use and faster convergence. Okay, if you recall in gradient descent, if the steps were small, then the convergence was more going to happen, not result in oscillations. But the convergence was slow there. But over here, the convergence is fast. So that's the difference. Now, temporal difference, online adaptability makes it particularly well suited for the environments which are in real world, which are dynamic, and where the agents have to learn and at the same time act also. So this is done simultaneously. Now, if you compare this with Monte Carlo methods, which are basically episodic, have a high variance, and have delays, now temporal difference is faster, it's more flexible, and it is often more effective in deep reinforcement learning settings. So, like it's a real-time responsiveness and the scalability that makes the that makes it foundational for what for many state-of-the-art deep reinforcement learning algorithms. So now we go into more details. So we start with the so before we start, I would just like you to take a look. So we have, as I said before, we have dynamic programming, and we have which consists of the models. We have Monte Carlo, which is more of episodic that we just discussed. So their overlap is temporal difference. So there's no model, and there is updates at every step. All right. So so we start with what is meant by bootstrapped updates. Now in bootstrapped updates, temporal difference learning updates, okay? So what it means that it estimates the value functions using partial return. All right. So what is the result? The immediate rewards plus the estimated value of the next state. So this is not like the conventional reinforcement learning approach where there are no immediate rewards. So what it does, this avoids the need for complete full episodes. Okay, and therefore, uh, and it allows for more frequent updates also. Now, what can happen? This can introduce some bias, uh, which also reduces the and it also reduces the variance. So as a result, there is an improvement in learning and there is stability for complex tasks. So in deep reinforcement learning, bootstrapping is essential for what? For algorithms like Q learning and actor critic, which we covered in topic number 10, reinforcement learning. And these are the algorithms that rely on approximating the future returns using neural networks. So, what is step by step learning? Step by step learning. So, temporal difference performs updates at each time step. So, that of course makes it more efficient in terms of performance and makes it more responsive than episodic approaches like we saw in Monte Carlo. And it also requires less memory and allows the agents to start learning immediately, even in tasks with long or like infinite, theoretically infinite horizons. Now, this kind of incremental update method is like specifically useful for deep reinforcement learning environments. Why? Because we need quick feedback and continuous improvement. Think of uh, a self-driven vehicle. Need quick feedback and continuous improvement. So this temporal difference approach enables fast convergence towards the say for example the global minima we're looking for, and it supports advanced techniques and batch updates also. All right. So that these are some of the advantages as compared to the Monte Carlo approach because this uses dynamic programming features also. Then is the online adaptability. So temporal difference learning algorithms, they excel in online environments. So where the agents must like adapt in real time. So how this is achieved? This is achieved by updating the value estimates at every step. Remember, it's a step-by-step learning approach, incremental. So that enables learning during ongoing interaction. So that like makes it suitable for non-stationary or evolving environments. Ideal scenario is a self-driven vehicle automatically finding its path under traffic conditions where the environment is changing and it's evolving and it's not stationary. So this adaptability is critical in scenarios such as robotics, recommendation systems, or game playing also, in addition to self-driven cars. Now, unlike Monte Carlo systems, which require completed episodes, uh, this approach basically can instantly react to new experiences. So that makes them highly effective for both an on policy and off policy learning, which we are shortly going to discuss. All right. So I would again suggest you to go through these details, okay, and also review these references. So we move to the next Q&A. So what is exploration versus exploitation, and what is the trade-off? So let's look at this scenario here. I'm going to explain this scenario to you. So what this scenario is is fairly self-explanatory. So we have like two friends, and they are digging for this diamond, and this friend discovers the diamond, and the friend thinks that the guy who got the diamond, who like has like walking away with their diamond, so he starts using that site, and if he had uh, did some more digging, would have discovered a larger diamond. So that's a trade-off. So what is that trade-off? The trade-off is exploration versus the exploitation. So there has to be a balancing strategy, right? So there has you need to balance it. So if we go into a little bit of details, what I just mentioned. So say for example, your friend and you are digging in the hope that you will get diamond out of it. Now apparently your friend gets lucky and finds the diamond before you and walks away happily. Now when you saw this, you got a little greedy and think that you might also get lucky. So you start digging at the same spot as your friend. Now what you are doing is called as the greedy action, and it's called as the greedy policy. However, the greed is not guaranteed to succeed. In this case, it would fail because a bigger diamond is buried where you were digging in the beginning. However, when your friend found the diamond, the only knowledge you got was the depth at which the diamond was buried, and you do not have the knowledge of what lies beyond that depth. But in reality, the diamond may be where you were digging in the beginning, okay, or it may be where your friend was digging. It could be here also, or it may be completely at a different place. That is also a possibility. So what is the exploration and exploitation trade-off? This trade-off is fundamental to deep reinforcement learning, and it shapes how agents gather information and maximize the rewards. Remember, reinforcement learning is about rewards and penalties. So exploration derives learning by exposing the agent to unfamiliar parts of the environment. That is exploration. While exploitation ensures reward optimization based on the current knowledge. Now, if there is no proper balance, agents either miss better strategies or fail to benefit from what they have learned. So, strategies like Epsilon, Greedy, Softmax, and UCB are the standard ones, and they provide the mechanisms for achieving this balance. Now, recall this trade-off also influences the behavior of temporal difference and Monte Carlo learning methods. How? Because temporal difference favors incremental exploration, while Monte Carlo relies on broad exploration. So there has to be a trade-off. Ultimately, managing this trade-off will lead to better performance, will lead to faster learning, and will lead to more resilient policies. So now let's go into some more details. Okay. So the need for exploration. Now, exploration enables the agents to learn unknown dynamics, uncover hidden rewards, and prevent premature convergence to suboptimal strategies, like stopping at the local minima while looking for the global minima. Now, this is especially true in complex or sparse reward environments where the agents must explore sufficiently to build a complete value map. Now, using the techniques such as epsilon greedy, which we like saw about the grid here also, or curiosity driven exploration that facilitates this. Now, remember that without exploration, deep reinforcement learning agents may miss critical states that impact long term performance. Okay, so that was exploration. Now, what are the rewards for exploitation? Now, exploitation rewards they leverage on the agent's current policy to maximize immediate gains. Now remember that as the value estimates become accurate, exploiting known information leads to efficient, better learning and higher rewards. Now remember that excessive exploitation without exploration can cause overfitting to suboptimal paths. So now we're looking at the search space. Now in temp- in temporal difference learning, exploitation aligns naturally with bootstrapping. How? Because the estimated values guide the agent's behavior in a greedy fashion. So there's a inherent match here. So if you look at, so we need to do a balancing strategy. So what is the balancing strategy? Balancing ensures the agents don't explore endlessly digging and digging and nothing is discovered, or exploit too early, or start looking around. Now, like methods like epsilon, greedy decay, softmax, and UCV, they adapt the intensity of exploration based on the learning progress or uncertainty. So, what is the right strategy? The right strategy improves sample efficiency, it improves conversion speed, and it improves the policy quality also. Now, in deep reinforcement learning, these balancing methods integrate with policy optimization frameworks to do what? To handle high dimensional state spaces, which is a reality, and work with noisy feedback efficiently, because that's what real life is.